Okay, let's try with the next few pages. So take your time, do question 10, 12, 14, 19, and 22. So 2 page also. Pause the video now and do it first.
2,000 years later.
Okay, so let's take a look of the first question that we have. It said the car traveling at this speed, and then the car driver sees an emergency, and then 0.5 seconds later slam on the brakes. So you need to be careful with this. What it means is a type of question called the braking distance, and there are two parts. So usually the shape of the velocity time graph looks more like this, where you take some time, like reaction time in here is 0.5 for reaction. So this is called the thinking time. You should have learned it in IGCSE, and this is actually the braking distance. So the whole thing is called the stopping distance, and so the actual distance to travel before the car stops. So the deceleration is 4, and when it stops, of course, the velocity will be 0. So you want to find the total s. So the first thing you want to find is maybe the first part of s. Let me just call it st. How about that? Thinking distance. So that will be the time before 0.5 seconds, and there's no deceleration yet. So the calculation would simply be 40 times 0.5, though, so that will be 20 meter. And then for the braking distance, because you actually apply the brake, and that would be calculated by using, you have A, V, U, S, and you got T actually. So shall we, actually there are different ways to do it. So I would prefer using V square equal to U square plus 2AS, and then V is 0, U is 40, because you may want to use V in your equation because it's 0, 0 is just nice to calculate. U is square, and then 2A is 4, so be careful, this 4 is not positive 4 but negative 4 because it's deceleration. And then S, and by using your calculator you should find it is 200 meters. So in total this is braking distance. So I'll put B here. I won't put B here because this is a more general displacement. So only I substitute, and this will be the braking distance. So in total, the so-called the stopping distance will be 220 when you add these two together. So that's part 1. Part B, calculate the stopping distance if the driver could apply the brakes instantaneously without reaction time. So that will simply be 200. Okay, if this is really in the exam, although I don't think it is, you could explain a bit more, but apparently this is simply 200. C, calculate the difference in your answer to A and B. That would be 220, and that is simply thinking distance. I don't know why they should actually ask like B first maybe, and then C and maybe A at the end. Assume now car is traveling at a 30 meter per second square. Sorry, per second only. So basically it's slower. Instead, without performing any calculation, state whether answer in C will be less, equal, or larger. Well, of course it is less. Alright, this is like common sense. Referring back to the graph, you can imagine it was 40, and then now if you're traveling at 30 and then maintaining other things the same, then say reaction time is the same, so then maybe I zoom in more. Then you could have 30 here as the reaction time. And what about the next part? In the next part, you should be able to know the slope is the same because the slope represents acceleration in VT graph, and assuming in our case now the deceleration is remain the same as 4, so then the slope will be the same, and the shape should be like this until the velocity becomes 0. And so in order to know about the distance, then you can compare the area of it, and you can apparently see the green area is smaller than the red area. So that is why it is very influential that driver should obey the speed limit to keep yourself safe. So that will be the explanation. I'm not going to type or write here. I think I'll just explain verbally. Let's take a look at the next question. So it says for a particle moving in a straight line and in acceleration, so you have acceleration, this is a straight line. There are cases where you may move in a circle. We will learn in chapter 6 after chapter 2, called the circular motion. But here we only consider straight lines, so 1D problem. With the time shown in the diagram, initially velocity is 2. Okay, so this is an AT graph, be careful. Find the maximum velocity reached. So since all this is AT graph, and then you know under the area, the meaning of the area will represent by the idea of acceleration times t, or integrate A with respect to time if you want to know, or simply just A times t. So in that case, since all these are positive area, positive as in it is above x-axis, below x-axis will be like negative area. Mathematically, of course, in practice, in daily life, you can't have negative area. So in that case, all these should be counted, and by 6 seconds, you should have the maximum velocity. So calculating the area, then this should be 2 times 3. This should be 2 times 6. So 6 plus 12, that makes 18 meter per second. Together with the original 2, then for part A, allow me to just write in formally. That will be simply 20 meter per second. You should get the idea. You just add them up together. Or if you really like to, you can simply do, just simply add, I would say. Draw the graph of the velocity versus time. Okay, so this is a challenging one. And since we know it is going to be positive throughout, then we only need the positive side of the domain for the velocity. So it starts off with 2 and it ends with 18. So let's set 18 to be the maximum, somehow maybe here. And then we just have to think about what happened by each part. So for the first 2 seconds, let's say around here, it is there's no acceleration, so velocity remains the same. And then afterwards you have 3 meter per second square for 2 seconds. So by 4 seconds, and then you can see it is 6. So 2 plus 6 should be 8. So maybe around here. And the only thing you have to think about is whether or not it is a straight line, or a curve like this, or a curve like this. So I would say by each second it increases the same. So since acceleration is constant in these 2 seconds, then the slope of 3D graph, since it represents acceleration, should also be straight as well. And then lastly, it is the same idea where you from 4 seconds to 6 seconds, you have the same acceleration, which is 6. So you should be having a straight line also. And one thing that you should notice is that the slope of this segment versus the slope of this segment, from 4 seconds to 6 seconds, this one should be steeper. And that is because of the value of the acceleration is 6. So while this one, the slope should be 3. So if you try to kind of compare their slope, then of course later on will be steeper. So this is question 12. Let's take a look at the next question. So here is that there is a position of moving object with time. Draw the graph showing the variation of velocity, time graph. So this is speed time graph. And how about I just draw it on top of that? Shall I? Maybe not. Maybe I'll just draw it next to it. So you have started with 0. Actually, from that you can already tell it is the slope, right? You can then kind of translate into velocity. So anticipate there's negative slope here, so I should prepare the negative domain of v, and so 0 is here, and then by 1 second, because the whole thing is 3 seconds, by 1 second the slope is 0, so for sure that I will have a slope like this. And then I should have find the slope for each point. Then I think I am supposed to sketch only, right? So I think I'll just roughly, I don't want to do any calculation on this. And so initially it is very positive, and then lately is less and less and less, and then become negative. So I believe it should be something like this. Okay, while initially it is positive, and then at 1 second becomes 0, and then lately it become very negative. So you should anticipate in the second the, if say this is a certain value, say it is 4, okay, then here should be -4, because apparently these 2 points are kind of like, if you look at these should be symmetrical. So yeah, I think I draw pretty well here, pretty much symmetrical, and then this should continue further. If you want to calculate the slope, I'm pretty sure there is a way to do it also. Let's take a look at the next question. We have a graph of VT graph, and then it asks you to draw the acceleration time graph. And I have a note here, treat the y-axis as displacement instead. So oh yeah, in this textbook sometimes they have quite a lot of typos, so you may need to be very alert all the time and think deeper. I like to have textbook with typos somehow, because it helps you to, like what I said to you guys, always to be skeptical and think twice. And for this case, if we keep it as v, what I think is it will be quite difficult to think like of the result. So I think treating it as displacement would be the one that usually expected in IB. I'm not saying that it is impossible to do with a VT graph like this, but it's just probably more expected to be like this. So here, this is in fact a very common shape of the DT graph, of when you float something upward and then it just simply come back down, right, over time. So I do believe the acceleration is simply a constant, and you should be able to see it start off with a certain positive value of v, and then here the velocity becomes 0, and then velocity become negative in this case. So acceleration is like, I think it's like gravity, so it should be a negative value. Oops, some more patient. So should be more like a negative value, simply constant number, so like g maybe, and that is pretty much it. Okay, last question of this part of video. It asks you to sketch the VT graph for 3 different cases. No numbers are necessary. Yes, okay, sure. So for the first one, ball drop from a certain height and bounce off a hard floor just before. First of all, you need to notice this drop. Drop means initial speed is 0. The speed just before each impact is the same as the speed just after impact. So actually this is a very important sentence you have to digest. It means v equals to u, right? So no energy loss, in other words. Assume the time of contact is negligibly small. Okay, so let's see, there should be positive and negative because you go up and down, and let's say going down is negative. So I suppose it was negative first, and then when it going down is positive, right? Going down, yeah. Going down is positive, so it should have 0 velocity at the beginning, and then it go faster and faster downward, so it will increase up to a certain point, because the slope here represents the acceleration, and that is dependent on the gravitational strength, which is 9.81 on Earth, and so it will be constant when you are near the Earth's surface, so a straight line. And then when it hits the floor, I don't know how far it is from, so let's say this is a point where it hits the floor at a certain distance, and then it should bounce back up. And since the question said the speed is the same, but then when you bounce back, it will be opposite direction. So if I say this is a certain value, say it's k, then you should find a similar scale, negative k here, and then you should start off your speed right here, I mean velocity here, and then when it go up, it would experience the same deceleration or acceleration, you may call, which means the slope is the same. So then you will have something like parallel to this. I try my best to draw, so I think I draw pretty well given that I'm on a computer. Okay, so then that is what happened when it reached the highest point, because the velocity is 0, so then it will continue to extend, because by the time the ball reached the highest, it would come back down, and then similar to the first segment, after a certain distance, then it will hit the floor again. So hopefully I could have this part, okay, actually I draw a bit too long here. So these 3 segments should have the same time. So if I call this 2, 0, 2, 4, 6, that could be example, or 3, 6, 9 maybe. Okay, so that is for part 1. For part B, the kart slides with negligible friction, so no friction, along the horizontal air track. The kart hits the end of the air track in reverse direction in the same speed. So in fact this is a bit similar, but then this is without any gravity, because it's a horizontal movement and there's no friction also. It had right before the impact. Assume the time of contact is negligibly small again. Okay, so in this case we can maybe assume to the right is positive because it's a horizontal movement. And then for the graph, let's say it is moving to the right at the beginning, so it should have a constant velocity, because again there's no friction, there's no other force literally. So according to Newton's first law, you learned velocity should remain constant, so a horizontal line until it reach the wall. It will bounce back. When it bounces back, it go back to the opposite direction, which means it's negative. So negative here with, I suppose, actually I don't know how the setup is. Are we supposed to have like a wall like this, like a cart, and then it bounces back and forth like I don't know. If that's the case, then you may have the same length. Alright, if only one wall, then you can just stop at the first part. But I think overall it just looked like something like this simply. Okay, constant speed throughout. Last one, a person jumps from a hovering helicopter. Hovering means it is kind of stay in the mid-air without any movement at all. So no acceleration, of course even no velocity. This is reached, like a bit off topic, this is reached by having the gravity. So imagine the helicopter, okay, I'm not going to draw here, but then usually in physics we use simply a circle to represent an object. Its weight and its lift force is equal. But of course, in reality, the helicopter is much more complicated, because the rotary blade would exert something called a torque onto the helicopter. So that's why you see there is a tail in the helicopter, and it's much more complicated than that. And also the lift generated by the helicopter may not be exactly 90 degrees. There are some other things to consider. But anyway, this is the simplest model to think about how helicopter code for. And the question said after a few seconds she opened parachute. Okay, eventually reached terminal velocity. And so this is about the terminal velocity, about the parachute cases. So okay, so let's say going down is positive, so we could have, it's always going down, so it's always let me just utilize the line here. Okay, it's very strict. And so we start with 0 because she jumped off from the helicopter, and then it starts to accelerate with a certain acceleration which should be very close to 9.81. And when the speed is small, the air resistance should be quite small. But since velocity start to pick up, then let me draw a free-body diagram. Then normally you have weight only, which gives you acceleration of 9.81. But then since you speed up, then you should start to have air resistance. Because just a quick revision, air resistance has two factors. One is the speed. The faster speed you have, the greater air resistance you have. The other thing is the surface area, or the shape. Shape is like another kind of geometrical features. So in this case, then the acceleration would be less, so not as steep until it reach 0. So this is kind of like the first terminal velocity that she reached. And then after a few seconds she reached open the parachute. So in fact, I actually don't know whether she reached terminal velocity. Let's say she did. Okay, so after she opened the parachute, then air resistance will be much enormously greater, since surface area suddenly increase. And so this one suddenly increase, even greater than weight. So in that case, the velocity would start to decrease. But then since velocity is decreasing, then the air resistance, which is pointing upward, is also decreasing. So then you will have a graph something like this at the end, and eventually the air resistance will be again the same as the weight, and so that will become the steady speed that you have, and that is the terminal velocity. So the whole graph should have two segments. One is this curve, and the other one is this curve, and then it level off at a certain constant value. If you can't actually visualize this, I would recommend you to watch another video. Here is a very nice video made by, I think, a documentary, and you could take your time to watch it. And basically the graph that we just now drew is describing what happened here. So try to get your time to maybe watch it over again. Although you should have watched it maybe in IGCSE physics. And notice the relationship between the two forces will basically affect the acceleration and hence the velocity.